Okay, thank you. So, well, first of all, it's a pleasure to be here again. I mean, I spent many happy months in the Schrödinger Institute in the past, and I'm very happy to be here again. And thanks to the organizers for the invitation. I don't want to rewrite. I mean, the title is sufficiently vague that I don't want to write it again. But I want to make sure that this is joint work with my PhD student, Girish Vishwa, and the work here that is joint with him, and the work that isn't joint is his work. So, but he's not here to defend it, so I don't want to put him on the spot. Anyway, so the plan is basically, I break it up into three parts. First, I want to talk about, so it's going to be a talk about CFT, I'm afraid. And I had a misspent youth spent on conformal field theory, and I hadn't gone back to it for a while. So for me, this is a bit of mathematical archaeology. I had to kind of, go back to my youth in some sense, mid-90s when I was a young postdoc, and refresh a lot of the stuff that I'd done then. But it's been kind of fun, but it's not something that I've been thinking about for the last couple of decades, actually. But anyway, I want to first talk about the algebras of interest. These are this BMS-like algebra, so it's a generalization, if you wish, but it's well studied in the mathematical literature to some extent. Then I want to talk about the semi-infinite complex, or in physics we call it BRST cohomology, or BRST complex. And third, I want to talk about some embedding theorems. So I'm not computing any BRST cohomology here. That's something that we have planned in the future, but so far we're just setting up. That's the plan. Please interrupt me at any moment. I'm happy to answer questions. I realize that this is not a VOA community, so maybe there's some stuff that maybe not so familiar. So please ask, and I'll do my best to explain. Okay, so algebras of interest. So we start with the Witt algebra that in physics is known as the centerless Virasoro. Mathematicians like to think of it in a slightly different way, but so you can think of it as centerless Virasoro. You can also think of it as follows. If you consider the associative algebra of Laurent polynomials on, say, one complex variables, then Witt is the derivations of this algebra. So Witt is the, in other words, it's polynomial vector fields. So there's a standard basis, everybody knows, minus z n plus 1. Round d here means always derivative with respect to this variable. And the algebra that everybody knows, it's ln, lm, minus m, ln plus m. I hope everything is familiar for now. Okay, so now we consider so-called tensor density modules. So these are, I'm going to consider only one special type. So I'm going to consider something that typically goes by the name of I lambda, and I'm going to moreover think of lambda as an integer, although you can, of course, take lambda even to be a complex number. So what is this? These are the tensor, so-called tensor density, well, a special kind of tensor density module. So it's a module of this algebra, and it's spanned by things that look like dz to a lambda. Right? So the module is A acting on these guys. In other words, typical elements in here will, well, I mean, there's one for every integer. So we can think of this, if you want, as a vector space as, let's call this, as in BMS, let's call these guys Mn. And, you can see how these guys act on that. And the algebra that you find is ln, lm, sorry, mm minus, I guess, m plus lambda n. And then you declare this m's to commute. So this is just a standard extension of the algebra by a module. You get a semi-direct product with the module being abelian. Okay. So this algebra, it's typically called G lambda in the literature. -1. Yes. So right. I will mention this in a moment. But okay. So this guy is going to be Witt semi-direct product this I lambda. M has conformal weight 1 minus lambda. So, so for example, so if you want to keep in mind BMS3 is well, BMS3 without the central charge. So it's going to be associated to lambda equals -1. For example, lambda equals 0 is the so-called, well, once you centrally extend, is the so-called Heisenberg-Virasoro algebra. Okay, okay, but this is centerless, right? There's no center here. So what about central extensions? Yeah. Yeah. Yeah, you're tossing in a bit primary of weight 1 minus lambda. Okay. I mean, this, you know, let me not mention this, but I mean, in the representation theory of Virasoro, if you want to understand the embedding diagrams between, say, Vera modules and stuff, then it is convenient to actually consider more general density modules where you consider two complex numbers, alpha and beta, let's say, and then what you have is the module that is spanned by z to the alpha, dz to the beta, where alpha and beta are complex numbers. And then depending on their values, there's an intricate relationship between these. But here I'm doing something very simple. I'm just taking lambda actually to be an integer and nothing in there. Physical perspective, what do you mean this does make sense? You mean negative conformal weights? Yes. Yeah, I mean, depends. So if you want to build, I suppose, a unitary conformal field theory, then you would have difficulty doing that. But I suppose, yeah. I mean, we haven't. Okay, for that you need to really study the representations of this algebra. So it has different kinds of representations. I mean, it's a complicated algebra. So it has highest weight representations, weight representations, which are not highest weight, but which have weights, and then it has even non-weight representations. So it's a complicated beast. But I guess in physics, typically we would be considering highest weight and representations and things you can resolve in terms of highest weight representations. Yeah. Well, highest weight, yeah, okay, sure. Non-weight representations is the ones where the carrier space of the representation cannot be written as a direct sum of weight spaces of the zeroth part of it. SL2 has non-weight representation. They're not very common in physics. We don't normally see them, but the simplest, SL2, I mean, 2 by 2 matrix determinant 1 has non-weight representation. And in fact, they've only recently been classified in the last 10, 15 years. Excuse me?
Are you going to elaborate on the possible cosines?
Yes, I'm about to do that now. Okay. Yeah. So central extensions. Yeah, that's the first. Okay, so central extensions, they're essentially classified up to equivalence by the second Chevalier-Allenberg homology. So this classifies central extensions up to equivalence, by the way. So it's important to distinguish that, I mean, not that I'm going to make a big deal of it, but it leads to some confusion that when you do this, you're not classifying central extensions up to the algebra isomorphism. You're classifying central extensions up to equivalence, which are special kinds of Lie algebra isomorphisms where the algebra you're extending and the thing you're extending by remain inert. So it's a slightly, no, but anyway, classifies central extensions, and you can compute this. And this is originally a calculation that Girish did with another PhD student, Lucas Buzaglo, in Edinburgh, who is a student of my colleague Sue Sierras in algebra. But in fact, it turned out to have been done earlier. Yes?
Could you have non-central?
You could, of course, yeah. I'm not going to mention them because I haven't looked at it. But I can tell you I can tell you the answer for this. So this result of, well, I don't know who is due originally, but Girish then found it in some paper. But basically, this could be three-dimensional in the case that lambda is 0 or 1. It's two dimensions in the case that lambda is -1, and this is BMS3. And then it's one dimensional for any other otherwise. I'm going to ignore lambda equals 0, 1. So I'm going to consider basically, I'm going to write things for lambda generic or lambda equals -1. So, let's say, so let me ignore 0, 1 for the purposes of this talk. And so this is the central, this is the universal central extension. And the algebra is, well, what you would expect. Just add, okay, so this one that always exists, of course, is the Witt central extension. That is the Gelfand-Fuchs cocycle that gives rise to the Virasoro algebra. Should we call the Gelfand-Fuchs algebra because they did it much earlier, but okay. In physics, we call it Virasoro. So that's always there. So let me write it. So ln delta n plus m. Then, okay, ln. So I'm going to write, so whenever I write something in red, it's going to be the lambda equals -1. Just to, it's not there unless lambda is -1. But basically, well, okay, let me write it at the end. So, so this one is going to be minus n plus, sorry, m plus lambda n, mn plus m. And then this is the lambda -1 thing. Okay, so the first thing I'm going to do, and just because we can, in some sense, is to, it's kind of complicated, I find, to work with modes. So I prefer to work with operator product expansions. So what I'm going to do is I'm essentially going to introduce some fields, toss in some normal, some formal variable, and consider it's just because there's two more central terms that I don't want to have to worry about. It's for exposition. It's just that I don't have to write the full thing. Lambda is 0 is Heisenberg-Virasoro. So you're tossing a U1 Kac-Moody, and indeed the central extension is precisely the Virasoro, U1. Okay. Good. So right. So z minus n minus 1 minus 1. Okay. Very good. Once you do that, then you can sorry, and I forgot to, of course, say that Mn, this remains regular. Okay, so from now on, I'm just going to simply work with OP. So let me just write them once and for all. So this is going to be here's the identity. Where I'm going to write the identity explicitly. And sometimes, by the way, I may introduce a notation, typically sort of in VOA technology, that if you have two fields, then the bracket sub n is the nth order pole in the OP of A and B. So I may introduce this a couple of times. But okay. right. Okay. Right. No, no. These are, what I mean by this is sort of just isomorphism of algebras. All right, okay, so continuing with this, write it in red. I'm gonna regret the color coding in a while, but okay, at some point I'll stop, but I mean, I just, I say dot, 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 I just mean regular terms. And okay, so these are the, and okay, the red thing, this is again, red means lambda equals -1. Okay, so those are the algebras of interest. Any questions on the stuff that we're going to? Yes, you're right. I should not put a 2. I was running ahead of myself. Very good. 1 minus 1. Thank you. I was running ahead of myself. I don't know why I put a 2. Yeah. I don't know. I mean, there's that's I suppose. Yeah, I mean, it'll be some extension of SL2 by some module. In the case of -1, you have the adjoint module, which is interpret as translations. If you think of SL2-1 as Lorentz, in general, it's just going to be the extension of SL2 by some module of certain. Maybe, I don't know. I mean, I haven't myself. I haven't looked at it, but I'm sure you could. Yeah. Okay. Right. So that's part 1. So so the semi-infinite complex. So I'm not going to define semi-infinite cohomology. That would take a whole hour probably to do it properly. But let me just mention a few words. So if you have an algebra which is Z graded, even superalgebra, but okay, let's say Z graded, and such that, let's say the dimension of each of the graded pieces is finite, then Feigen introduced a kind of cohomology theory which would agree with the standard cohomology theory of the algebra of finite dimensional, but if not, so he introduced something called semi-infinite cohomology. At a very high level, if you think of Chvály-Eilenberg cohomology as kind of a derived functor of invariance, and the algebra homology as the derived functor of co-invariance, this guy is kind of an unholy mixture of both of those things. Luckily, we don't have to go through the definition because if you are happy with computing semi-infinite cohomology relative to the center, then this is what in physics we call conformal field theory is typical BRST cohomology. So this is kind of, it's a general theory which one can prove very general theorems about semi-infinite cohomology. Famous paper in the mid-80s was Frankel, Garland, Zuckerman that essentially interpreted the calculation of the spectrum of the bosonic string in terms of the semi-infinite cohomology of Virasoro relative to the center. And it is cohomology with values in some representation, and the representation is the matter conformal field theory that you are studying, right? So this is kind of the right language to discuss at least a spectrum of of different string theories. Anyway, so I'm not going to define it properly, but all I'm saying is that it's so semi-infinite. Let me introduce a notation. So the notation is well, semi-infinite, but people put infinite. Yes.
So physically, this is what you want to try.
I suppose yes. Eventually,
that is
that's why I got into this.
Okay.
So the notation is, I'm not going to define the actual complex, but I'll introduce a notation just so that I can refer to it. So we normally compute this with respect to some representation, but I'm particularly going to be interested in so-called relative cohomology. So if this is the center of G, I'm going to be interested in this thing. So relative semi-infinite cohomology relative to the center with values in some representation. And this is what in physics we typically, or in the CFT case, we call the BRST cohomology. So okay, so how do we do this? Well, let's look at G lambda. So we're going to take G hat lambda, and the way you compute, you build the BRST complex is, well, you introduce ghosts, so fermionic BC systems. In this case, this is a Lie algebra, so all these are fermionic BC systems. Otherwise, the statistics of the BC system is opposite to the statistics of the field. We have two fields. We have T and M. So we introduce two. So we introduce a fermionic BC system of weights 2 minus 1. These are the ones corresponding to T. And other ones, which I'm going to call BC, capital like that, which are the ones of 1 minus lambda and lambda. And so these are the ghosts. And if you want, these are the ghosts for T, and these are the ghosts for M. Let's assume, yeah. So if you want to interpret the BRST cohomology as the spectrum of a string theory with gauge principle being this algebra G hat lambda, then this would be the calculation of the spectrum of the. Correct. Correct. Excuse me? It would be an old string, yes. But there's going to be a kink in the.
Among applications,
Correct. That's a different. In fact, in the context of asymptotic symmetries, as Arjun reminded us yesterday, it turns out that the precise BMS algebra that you get does not have a semi-infinite cohomology, an obstruction to the existence of the complex, which I'll mention as I go along. But anyway, so the idea is that once you so this is how you to by stepping the whole Feigen story, you essentially introduce this ghost. These are going to be fermionic because we're dealing with a Lie algebra. If it was a superalgebra, then some would be fermionic and some would be bosonic. But okay, in this case, they're fermionic ghosts. And then what you try to do is you try to construct a BRST current, which typically starts with, I'm using notation, these brackets mean normal order product, and my normal order products are always associating to the left. So if I have three things, notation, just put it here, so normal order product. So, so this would be the regular part of the OPE between, the first regular term in the OPE between C and T, for example. But if I write something like ABC, really what this means is A normal order product BC. So I'm always associating to the left in case I need to write. And the other one would be C with M. And then you put dot 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 with these are some trilinear in the BC's stuff. And the fundamental property that you want of this operator is that if you define D, sort of differential, sometimes called Q, which is the first order pole with this current, then d squared is equal to 0. And this current, you want to have two properties. You want to have conformal weight 1 and ghost number 1. And the ghost number assignments is this has ghost number -1, so this is ghost number. This has ghost number 1, this -1, this 1. You want a conformal weight 1, ghost number 1 current, which starts like this with some trilinear stuff. And the fundamental property is that if you look at the first order pole with this current, and you define this operation D to be that, then first order pole with anything is always a derivation of the VOA, of all the brackets. So this is some sort of derivation, but you want it to be 2 squared equals to 0. This D is what we would normally call the BRST operator. And this representation M is some representation which is D and M. Yes. Say that again. No, you won't. So all I'm saying is that this is what we would like. Sorry. Would like. So now let's see whether in fact we get it or not. Okay, so the first thing is the first thing is the following. So we can actually do this for G lambda, generic lambda. Now in generic lambda, remember these red terms are not there. So what we need to do essentially is to find a representation of G hat lambda on the ghosts. So one can work that out. So let's write T ghost. Well, T ghost, we know what it is because we know what the conformal weights are of the ghost. So there's no choice here. So this guy is the natural one. So -2, I'll write it, BDC minus DBC, and then minus because it's fermionic, 1 minus lambda. I'm going a bit slow. Please interrupt me anytime. And I think what I'll do is I'll try to just keep going, and then you can kick me out whenever you want. I'll try not to run too, but just to do things carefully, I suppose. Okay, so that's the standard energy momentum tensor of two fermionic BC systems with those conformal weights. And then you can write this guy, and this looks like lambda minus 1 DVC minus DBC. So it's the capital B and the lowercase. Yes, because I got, I went and, I got distracted because I went to turn off the fan. That's already written, so sorry. So what I want is just lambda dBc. This isn't erased very well, so maybe this is not the canonical eraser. Is this one? Yeah. All right. Once I define these things, I can construct this BRST current. This looks very familiar if you are familiar with the one in bosonic string, for example. And d squares to 0 if and only if the central charge is equal to 26 plus twice 6 lambda squared minus 6 lambda plus 1. Okay, that's for generic G hat lambda. So it has a semi-infinite complex, and that's the BRST differential, provided that the central charge of the module that you consider takes this form. This is precisely to cancel. So the reason for this is that if you consider the total energy momentum tensor, which is the BRST variation of the Virasoro if you want anti-ghost, and m thought to be d of the other guy, then t thought and m thought, they satisfy g lambda without the central extension. So what you're doing is you're canceling the central extension of the matter system, if you want, of T and M with the central extension of the ghosts. And as you know, the ghosts have minus 26 minus twice. Okay.
But it was -1.
Right. No, let me tell you what happened. So okay, so then the question is, I should probably write it in red. What about lambda minus 1? Well, so you can do the Feigen story, and Girish shows that when you do this, there is no semi-infinite cohomology unless the central charge that you would expect, the Cm, is equal to 0. But you can actually see this also in this language in the following sense. Let's try to find a representation of g hat minus 1 using this ghost system. And there turns out that there's precisely one. So you can consider the following object. So Cm divided by 54, okay, so just this. But so you have this quartic term, which is a problem. There's some, okay, I'll write it, but I mean, it's a complicated total derivative term. Remember, you want to make this to be regular with itself, which requires some correction. But this works. Okay, so this guy satisfies this m goes together with this one. Well, this one when lambda is minus 1 satisfies the g hat minus 1 algebra with values CL equals to minus this. Okay, so the statement is that the original T ghost and this guy, they satisfy this guy with CL equals minus 26 minus twice 6 lambda squared minus 6 lambda plus 1, and Cm equals Cm. That's why there's a Cm there. The main problem with this is that, okay, so if I define T thought to be the sum and M thought to be the sum, then in particular, M thought is not going to be the first order pole for any, I'm not even assuming that J takes the form that I wrote, but for any conformal weight 1 goes number 1 current. So even if you're not in the, not every differential that you write down is going to be the Feigen semi-infinite cohomology differential. But the point is, no matter what you write down, there's no conformal weight 1 goes number 1 field that will give you. And then there's a theorem of Fusun-Ackman that says that the d squared equal to 0 property is essentially, it's equivalent to this guy's written as, there's a theorem of Ackman's, an old theorem from the 90s that says that d squared is equal to 0 if and only if in this context dB and dB obey the centerless. In other words, for Lie algebras and even Lie superalgebras, d squared equal to 0 really says that you have the semi-infinite cohomology of Feigen. There's nothing else. These guys then satisfy the algebra. The point is that this object because of this quartic term, essentially, which is the thing that is necessary to give it a non-zero central charge, cannot be obtained. This is okay. So what I tried to do for lambda equals -1, I said, okay, let's find the realization of g hat lambda -1, so BMS3 if you wish, on the ghost sector. T, it's forced because you know what the conformal weights of these fields are, but then the unique M that gives you that, the only thing that gives you those OPEs right there, including the red terms, is this. And this term, unfortunately, cannot be obtained by BRST variation. That's okay. Yeah, so no, everything here has ghost number 0. Wait, because there's always equal number of B's and C's if you ignore the case, right? So BC. I mean, this is you know. So this has weight number 0.
Yeah, sorry.
Is
No, sorry.
no, I'm saying that this guy is satisfied because there's a CM especially explicitly there, and you get, by using the T ghost that I wrote down and this guy, you get a realization of G hat -1 with this value of CL and whatever value you want of CM. Just put. Well, normal ordering product with unit operator is identity.
That's of course, now it's clear, but usually.
So it's quadratic it's quartic in fields, I would say. M ghost is quartic in field. I mean, the highest term is quartic. Anyway, so the upshot of this is that, in fact, so the upshot is that there is a there exists you know this BRST complex for all G hat lambda, provided CM is 26 plus twice 6 lambda squared minus 6 lambda plus 1, and CL and CM if in the red case, in lambda is -1, CM has to be 0.
But you weren't discussing the lambda.
Yes, but I didn't want to. I don't have so much red chalk, so I didn't want to use everything red.
No, but you said lambda to -1.
No, but the upshot is that, in fact, for any lambda, you've got this.
Ah, okay.
This BRST complex exists for every lambda. And if you look at particularly the case of lambda -1, then you have the possibility of adding an extra term. But what I claim is that this central charge has to be 0 for the BRST complex to exist. Excuse me?
What is CL for lambda?
No, it's 52.
Not 0.
52.
Ah, good.
Two spin 2 things. So 26 plus 26. So okay, so in the red case, this is 52. This one? This is the okay. Sorry, this is the one of the ghost. Yeah, very good. I write like this. That way I can use that. So this is the one. This is the one of the ghost system. And then if you want to cancel the ghost cycle, then you have to ensure that your matter, the representation that you choose, has the opposite central charge. So plus so 52 in the case of BMS, which is what you would expect. I mean, if if there were such a thing, the fact doing it relative to the center really means canceling the central charge. And the central charge is only susceptible to the conformal weights of the fields that you have. Okay, null states where? In a Verma module, for example, or where? I'm not sure I understand that. What do you mean by null states? You mean in the BRST coboundaries? Well, I mean, the differential defines that. So of course, there's going to be a different differential than. Yeah. I mean, we still haven't done any calculations of BRST cohomology for these G lambdas. That's something that it's the next step in this project. But the only surprising thing is that if you want to do BRST for BMS, you need to have Cm is equal to 0. CL52. Yes. This is semi-infinite complex relative to the center, which is what the BRST complex is. The BRST complex, you never have ghost or anti-ghost for the central elements. You're always doing things relative to the center. You could relax that by introducing anti-ghost relative to the central element, but that's what we do. Y26 for Virasora. It's the same question. I mean it's the same calculation. It's the same reason. I mean, do you understand Y26 for the bosonic string? You can in the bosonic string with the usual Fock representation. Then you can of course also try to view that by doing light cone quantization and then checking that you have Lorentz invariance at the end of the day. But that's not what we're doing here. We're doing covariant quantization, we're doing BRST, and the critical dimension, in the case of the string, the bosonic string 26, follows by demanding that d squared is 0. Yeah. This is, yeah, okay, so for the NSR string, you get 15. For the W3 string, you get 100 or whatever. I mean, it's all kinds of funny numbers. I mean, okay. I guess I'm really running over. But okay, we're having discussion as we go, so I don't feel that bad. So let me just mention these embedding theorems, what do I mean by that? So I won't give any details because there's just a bunch of formulas, but and now I realize that I have, this is it. Okay. Okay, embedding theorems. So what do I mean by that? Is this the canonical thing or is? Oh no, the water. When I was in Bonn,
I can do it for you, and you can.
Yeah.
Just tell me when I should erase.
I just want to erase one board so that I can
Which
use
one?
it. Maybe not. Yeah, that one. Well, while you're at it, let's do 2 boards, and that way I can just. So maybe this one and this one, and that should be.
And this one.
Yeah. I used to do this when I was a postdoc in Bonn. Actually, I always liked this system, but in Edinburgh we didn't have anything like that. Too clean for Edinburgh. So we're in mourning, by the way, in Edinburgh because Peter Higgs died on Monday. We're getting all inundated by emails of condolences of people writing to the Higgs Center, and then we're getting copies of all the emails. So my inbox is filled with a lot of very nice messages from people all over the world. Yes, thank you.
Not that I erased the wrong one. Yeah.
Okay, no, but I mean, I guess this is sort of for, I guess I have to wait a bit until it dries, or
No, no, it's okay.
you sure? Okay, okay, good. So let's talk about. Huh?
Yeah, you have 12 minutes.
Okay, very good. So okay, so the one embedding theorem, there's a couple of embedding theorems that we prove, but let me tell you the one that I think is perhaps more interesting. There's one which essentially is a check on an old conjecture of mine from the 1990s. So I'm not going to bore you with that. But let me tell you about the following. So, so suppose you have a Virasoro. So back to bosonic string. So suppose you have Virasoro BRST complex. Central charge, if you want, 26. So, and you can compute the BRST cohomology, which is the semi-infinite cohomology of Virasoro, relative the center, and relative some matter representation with C equals 26. So this would be the spectrum of a chiral part of the bosonic string, and I claim that this is isomorphic, and in fact, it's isomorphic as a Batalin-Vilkovitsky algebra. But you don't have to worry about that if you don't want. It's isomorphic to the semi-infinite cohomology of G hat lambda relative to its center, let me call it differently from that, and a representation which is a representation of G hat lambda that I make by tensoring M with something I'm going to call V beta gamma. So this is so what does that say, by the way? So this says that any, let's say, left moving or whatever bosonic string spectrum can be embedded as a G hat lambda string with a particular representation. This is okay. This has several names. Perhaps the most at the highest level, this is an example of semi-infinite Shapiro lemma. And if you want, I can tell you more about the Shapiro lemma. The semi-infinite version was proved by Sasha Voronov back in something. But essentially, okay, so what is this V lambda? V lambda is a representation of G hat lambda made out of a bosonic beta gamma system. So this is beta gamma. This is a bosonic beta gamma system, and I can write down explicitly what the energy momentum tensor. So this is beta gamma system again of the same weight, 1 minus lambda lambda. So this is going to be now a plus because it's bosonic. This, for the case of BMS, for the case of BMS3, this is an old paper of Banerjee and Jatkar, Mukhi, and Naogi in 2015. So let me just say Banerjee et al. But for any lambda, you can do this. It's not difficult. This gives you a so it's bosonic. So it's a plus sign and then the standard. So this is V gamma is this representation of G hat lambda, which has CL equals to 6 lambda squared. And okay, and the way you prove this, I'll just give you a flavor of the way you prove this. This is a version of the homotopy transfer that Maxim was talking about yesterday. What you do is you consider the Virasoro BRST complex. So what does this have? This has T and it has B and it has C, right? This is the standard Virasoro semi-infinite complex. And then you tensor with what we call a Koszul topological conformal field theory, if you want. And what is it? you toss in, I guess, B, C, beta gamma, right? This beta gamma is that beta gamma. This BC and capital BC, these are the ones of the G hat lambda BRST cohomology, and then you can cook up. So the nice thing about this Koszul CFT, this Koszul CFT has a BRST operator, which in my conventions is C beta, capital C beta, sorry. This is the BRST current of this Koszul CFT. The nice thing about the Koszul CFT is that it has trivial cohomology. So if you look at the cohomology of this dk, right, the differential which is first order pole with this current, this guy is isomorphic to C if n here if you need to choose a picture for the beta gamma system, but once you choose a picture, then you get that this is C in 0 and 0 otherwise. You're choosing a picture. If you're not happy with pictures, forget it. But I mean, the point is the presentation of bosonic beta gamma systems are very degenerate. Any pictures, you have to choose one. For each picture you get this. Anyway, so then what you do is, so the way you do this is you, so what is it that you have here? What you have computing this is a BRST operator, which looks like, let me call it the BRST operator. This is the BRST operator of G hat lambda in that representation. And then I claim that there exists some operator R, some current. There exists. I'll tell you the formula if you want. Lambda minus 1 gamma B dc gamma dbc. Let's define R0 to be the first order pole with this guy. And then what you can do is you can do e to the R0 d lambda e to the minus R0. And when you do that, this turns out to be the Virasoro BRST operator plus the Koszul BRST operator. Yes, I'm done almost. So because you're conjugating by an automorphism, the cohomologies of these two operators are the same. So if you want to compute the cohomology of d lambda, what you do is you apply this conjugation, and you end up computing the cohomology of the sum of these two things. And you use something called the Kunev theorem, and this becomes the cohomology of Virasoro tensor the cohomology of K graded, whatever. But this guy only has cohomology in the degree 0, so this is isomorphic. So you get I don't know, P, I don't know. Hn d lambda is isomorphic to P plus Q equals N, P, and Q, but this only is non-zero when Q is 0, so it's really isomorphic to Hn. Anyway, so that's one of the embedding theorems. The other one is slightly more complicated. It's embedding, so I won't do it also for lack of time, but the other one is actually embedding this complex in, not this complex, but the BRST G hat lambda, the general one with a module of central charge 26 plus twice 6 lambda squared minus lambda plus 1. You can embed that in a way inside a so-called twisted n equals 2 superconformal field theory in such a way that the chiral ring of this twisted n equals 2 superconformal field theory agrees with the BRST cohomology of the G hat lambda. This is a conjecture of mine a long time ago, because I checked it with absolutely every single case that I knew. String theories of all varieties, topological field theories, conformal field theories of all varieties, that you could always do that. Any topological field theory seems to be embedded quasi-isomorphically without changing the cohomology into a twisted n equals 2. And of course, the details vary. You need to do a bit of work in each case to actually show that, but this works also for G hat lambda. So one more tick in the conjecture that I cannot prove. But anyway, so I think I'll stop here just because those things are just a bunch of formulas. So no point in. Okay, thank you.